Okay, so good afternoon to everybody. Good evening for some in Europe, or good morning for East United States, West United States. And so welcome to the seminars of the Group of Orbital Dynamics and Planetology in Guaratinguetá, Brazil. And today we have our guest is Natalia Rossignoli. She's a PhD student, concluding a PhD at the University of La Plata. And she's going to present us some of her results, or part of her PhD. And the topic is on impact cratering model for the outer solar system, assessing the main impactor population in light of observational constraints. So please, Natalia.
Thank you very much. Thank you for the invitation to give this seminar. I'm Natalia Rossignoli. I'm a PhD student at the Instituto Astrofísica de La Plata in Argentina. And today I'm going to present some of the results of my PhD thesis that we have obtained together with my supervisor, Romina Di Sisto, and my co-supervisor, Gabriela Parisi. So in this talk, I'm going to present our impact cratering model for the outer solar system, and particularly for this talk, how we assess the main impactor populations in light of the available observational constraints. So, modeling the impact cratering in the outer solar system is one of the main topics of my thesis, which is focused on modeling the origin and the evolution of the satellites of the outer solar system planets. And we think these satellites are very special because their impact histories can tell us a lot about very small body populations that act in this region of the solar system. These satellites may receive impacts from, for example, planetocentric populations that are unique to each system, or also heliocentric impactor populations that have their origin in very distant regions beyond Neptune. So all these populations have very small bodies and are very difficult to study. So this is one of the ways of studying these populations. So the observed crater populations are a very important part of our work because we need to compare our modeled crater distributions to the observed crater distributions. And luckily for us, most of these satellites are full of craters. So as we can see here, we have MIMAS, which I'm going to present later in the talk, which is a mid-sized satellite of Saturn. And here in this figure, there is the crater counts for this satellite presented, published this year by Stuart Robbins and collaborators. And as you can see here in this panel, this is the cumulated number of craters observed on MIMAS per square kilometer in terms of the diameter of the crater. And each of these curves corresponds to a different resolution of the images. So as you can see, it is a very difficult task to obtain the crater distributions on these satellites. But it is very important. For example, observed crater distributions or crater counts can be used to compare different terrains within a satellite. For example, you can have different types of terrains in one satellite, and comparing the crater distributions, you can see what are their relative ages or what kind of processes have affected each area. Also, you can compare different satellites and obtain their relative ages with the crater counts. And also, you can use an observed crater count and build the impactor population that would generate those craters. And with that impactor population, you can apply it to the rest of the satellites to see if this impactor population is representative of the whole system. And in the last place, we can also use it as the main calibrator of more numerical or theoretical works, such as the one I'm going to present today. So in this talk, I'm only going to present our results for impact cratering model for the largest satellites of these systems, so the Saturnian, Uranian, and Neptunian systems, and for those satellites that have radius larger than 200 kilometers. So this is because it would be too long to present the whole system of satellites, but we have already studied the smaller satellites as well. So in this talk, I'm going to present for the Saturnian system, 6 mid-satellites and Titan, which is the largest satellite of Saturn. And the main calibrators in this case will be these works listed here, which were made with the Cassini images. And as you know, the images obtained by Cassini of the surfaces of these satellites have very high resolution, which is very good because then the crater counts have very high resolution as well. But in the case of the Uranian and Neptunian systems, they were only imaged by Voyager 2, so the resolutions of the images are a bit lower than in the case of Saturn. And also, these systems have many crater counts available, but we chose those ones that have the most cratered areas of each satellite, and those that present the larger craters, because these larger craters are less affected in general by erosional processes, or they are primary instead of secondary, and we only model the primary craters. So how do we model the impact crater distributions on these satellites? Well, we rely on the results of our numerical simulation that was published in 2020 that follows what we think and model to be the most important impactors in these systems, that are the heliocentric impactors that have their origin in the scattered disk inside the Trans-Neptunian region. So essentially, this is our work from 2020. We chose 603 observed scattered disk objects, which are the family of origin that from which they originate, these heliocentric impactors, and we cloned these observed objects following an intrinsic model of the semi-major and inclination distributions. Why is it intrinsic? Because we built a debiased model of this distribution, because we understand that the discovery of these objects favors the ones that are closer to the perihelion. So we built an intrinsic model of these distributions for the clones, and we used the EVER code from Fernandez and collaborators from 2002, and we consider the current configuration of our solar system and a total time span of 4.5 gigayears. Then, with this simulation, we can obtain the encounter statistics with the planets. So, once they leave the scattered disk in the Trans-Neptunian region, these impactors are called centaurs. So, centaurs are the main impactors in our model. And using a particle-in-a-box approximation, we can obtain the number of collisions of centaurs with each satellite and the impact velocity. So until this point, this work is in agreement with other publications, such as the recent one by David Nesmorny and collaborators from last year. So we think these results are in agreement in general with the published results. Then we have to combine this with the impactor size frequency distribution, which I'm going to present next, and crater scaling laws. Crater scaling laws are the laws that relate the size of the impactor to the size of the crater. And these are calibrated in laboratories and experiments, and we use the ones published by Holzappen and Hausen for icy satellites for 2007, and the modifications for what is called a complex crater, which is a crater that has collapsed, which is large enough to collapse, and these were presented in Krauss and collaborators' work from 2011. So with all this, we can obtain our predicted crater distributions for each satellite. And as for the impactor size frequency distribution, many authors use different size frequency distributions. We use this power law, which has this shape for the larger members of the impactor population. where this number is fixed and is the estimated number of scattered disk objects with diameters larger than 100 kilometers. Then, for the smaller members of our impactor population, we use this shape of this distribution, where this index has a large uncertainty because these impactors are very small, so it is very difficult to obtain a certain impactor size frequency distribution. So the results I'm going to present will be in terms of these two limiting values between 3 and 3.5 for this index. The distribution looks like this. So for the smaller members, you will have two distributions, two limiting distribution, and for the larger members, only one distribution. So going into the results, as I mentioned, I'm going to present the larger satellites of these three systems in order of distance to the Sun, and inside each system in order of distance to the planet. And the crater counts you will be seeing will be these listed here. So going in now into the Saturnian system, we will see first MIMAS, which I presented before, which is the innermost mid-sized satellite of Saturn. And all the results I'm going to present will be in this format. This is the cumulative number of craters per square kilometer in terms of the size of the crater or the diameter of the crater. In black, our two results for the two limiting values for the size frequency distribution index that I mentioned before. And in color, we are going to see the crater counts presented in these works. Always, if they are available, the more highly cratered areas. And in the vertical lines, we see here in matching colors what is called the completeness limit of the crater count. So this means that craters that are larger than this limit are complete due to the image resolution that the authors used. So they are more reliable, the larger craters. And as the results you see here in the image, the 3.5 index is able to predict much better the observed crater distributions, while the 3 index generates an underestimation of the observations. And this will be a result that is repeated along the other satellites. So essentially, the 3.5 is better at matching the observed crater distributions on MIMAS. Then we have Enceladus, which is a similar size satellite, but is very active geologically, as you may know. And in this case, I'm presenting 3 different crater counts of the same work by Kirchhoff and Schenk from 2009. And these 3 different counts, I included them in this plot to show that one satellite can have very different types of terrain. In the case of Enceladus, in blue, we see the more highly cratered area corresponding to crater plains in the mid-latitudes of the satellite. In brown, we see a crater plain in the equatorial region, which these authors analyze and think that this kind of terrain is more affected by deposition by E-ring particles that favor deposition on the equatorial region of Enceladus. That is why, along the deposition of the particles, the craters may be obliterated. So this is modifying the original crater distribution. So that is why we always point to observe and fit the highly cratered areas less affected by erosion. And then I included as well the ridge plains on Enceladus in orange, which is thought to be much younger than the other terrains. So more craters have been obliterated in this area. As you can see, these crater counts are very different between the other. And again, we are seeing that our model for the 3.5 index is able to match the highly cratered area, while the model for the 3 index generates an underestimation. So in this case, we are seeing much better results with the 3.5 index. So going farther away from Saturn, we have Tethys and Dione, which are similar-sized satellites. And again, we are seeing that for the highly cratered area of Tethys and Dione, the 3.5 index is able to match the crater counts, but we see a bit of an underestimation here in Dione. And I will explain about this in the next slide. So what happens when we move even farther away from Saturn to very long distances, because Rhea and Iapetus are far away from Saturn. Iapetus is actually more than 60 Saturn radii away from the planet. And we are seeing here like a trend, like Dione, then Rhea and Iapetus. We are seeing that our heliocentric model is not able to match the crater counts, and this underestimation is growing larger as we move farther away. And this could be for a number of reasons, but in general, we consider that it may be because of, for example, other impactor populations are acting on these satellites, for example, planetocentric impactor populations, or, for example, as has been modeled in other works, a very early stage clearing of the primordial Kuiper belt. So this we have not modeled, but it is believed to have a very important role depending on the model you choose to build, and it may affect these satellites as well. But other possibility that we are starting to look into is that orbital migration in this system is very important, as has been presented in many works that model what is the rate of orbital migration of the satellites. And in this case, we think that if these satellites orbit more closer to the planet in the past, so they were closely packed together and closer to Saturn in the past, our model would be able to match the observed crater counts, because closer to the planet we would have higher impact velocities, so our model would move up and match these observed crater distributions. So these are different possibilities. We are studying what could be the better explanation for this difference that grows larger with distance, and we are aware that orbital migration may play a very important role in this system. And last, for the Saturnian system, we have Titan. I wanted to present it in last place because it orbits between Rhea and Iapetus, so it is not the one that orbits farther away, but it is very special because it is the largest satellite of Saturn, and it has a very dense atmosphere. It is very dense, and it shields the impactors, the small impactors, from reaching the surface. So as you can see, here is the observed crater distribution for Titan that goes flat for smaller craters. So in this case, we had to model and include in our cratering model the atmospheric effects on Titan, which was a bit tricky, but we managed to include some effects like, for example, drag, ablation, and the fragmentation of impactors that ended up being the most important of the effects. So if you want to check out more details, here's the work, and you can ask me later. But it was a very interesting work to do, and it was the first time we modeled the atmospheric effects. So now going into the Eurasian system, we have 5 classical satellites or mid-sized satellites. And here I'm going to present our results only for the 3.5 index, because the 3 index generates an underestimation, and it is so large that we do not include it in these plots. So for Miranda and Ariel, which are the innermost satellites of this system, we have in black our heliocentric model results, and in orange the crater counts presented in a recalibration of the Voyager 2 images that Michel Kirchhoff and collaborators made and published last year. So as you can see, in Miranda we have an underestimation of the larger craters, which is not very good. In Ariel, we see that our model matches most of the observed craters, but again, Ariel is believed to be affected by erosional processes that can erase the craters. So this would lead to an overestimation in our model. We would expect to have this black curve more overestimating the craters. In the case of Umbriel, as we move farther away from the planet, we see a large underestimation of our model, which is very alarming, and it's indicating that evidently the craters on Umbriel are produced or have been produced by other impactor population. So in this case, such a strong difference between our model and the observed crater counts, especially if it goes along or throughout all the crater sizes, is indicative of another alternative impactor population. And the same thing happened in Titania and Oberon. So these are very highly cratered terrains, and we are certainly not able to explain them with an heliocentric model. So we started to think what would be the possibility of another impactor population acting in this system. So we started thinking about the idea of modeling a planetocentric impactor population for this system. And as you know, planetocentric impactors may be formed after very large collisions that generate a lot of debris. So to explain the craters on these surfaces, you would need a lot of debris. So you would have to look into a very large collision. So having that in mind, we think that these recent works are very interesting to look into because, as you know, Uranus has a very large axial tilt, and a lot of works modeled this very large axial tilt produced by a very large collision. So, in very recent works, some authors have managed to explain the formation of the classical satellites from a debris disk formed after the large collision that tilted the planet. In particular, Jason Manchinois and collaborators in 2021 were able to reproduce the current configuration of the classical satellites with their current orbits and their current bulk densities. So that's a very interesting work because they managed to do all that simulating a large collision that tilted the planet, generated a circumplanetary disk of debris, and from that disk, the satellites accreted and formed. So that we thought was a very good starting point for our planetocentric source of impactors for these satellites. So in order to model this, we chose to model different types of planetocentric disks with different profiles or different particle distributions. And also using the EVORP code, we followed the dynamical evolution of these particles for 10 million years, which is more than enough in this case because planetocentric populations tend to evolve very fast. They collide with the satellites or with the planets or are ejected from the system in a few million years. So 10 million years for the dynamical evolution was more than enough to obtain impact probabilities for each satellite and each disk and the impact velocity. In this case, we started modeling 4 different types of disks with around 500 particles each disk, and we obtained very interesting results. But we had to combine that with an impactor size frequency distribution. And if you remember from the first part of my talk, the observed crater distributions can be used to build an impactor population. So we did that in this case in order to, with our planetocentric model, be able to fit the observed craters on Oberon. So we used the impact velocity obtained in our simulation and the observed crater counts published in 2022, which is this area of Oberon. And with that, we built a customized impactor population that would fit the crater counts on Oberon. So in some way, this model is tailored or customized to explain Oberon's crater counts. But what happens with the rest of the satellites? So in the case of Miranda and Ariel, the innermost classical satellites of the system, we see here in black our modeled heliocentric model, and in dashed lines we see the best case scenario of our planetocentric model. So as you can see here, this is explaining better already the larger craters on Miranda. In the case of Ariel, we produce with the planetocentric model an overestimation, which is expected if you analyze the images of the surface of Ariel, given that it is believed to have been resurfaced in a global scale. So those were good news as well. In the case of Umbriel, we produced a very good match with the crater counts on this satellite, so it is already a better fit to the observations than our heliocentric model. And last, for Titania, we see again an overestimation. So in general, in our work, an overestimation is not very worrying because you believe that these satellites may have been affected by tectonical processes and resurfacing processes in general. So you would expect to overestimate the number of craters because they may be obliterated, and also because you don't know where exactly those processes can act. So it may be a local process, but an underestimation is more alarming in general. So in this case, for Titania, we are not so worried about an overestimation. And of course, in the case of Oberon, the model produced a good match because it was tailored or customized to fit these crater counts. So in general, what we see in this system in particular is that the heliocentric model is not able to reproduce the crater counts, but the planetocentric model does a better job, but we are still looking into it to see what would be the best profile that matches all the crater counts. And also, I wanted to point out that with our simulation of the planetocentric particles, we were able to see that at the end of the simulation that we continued for 20 million years in some cases, some particles remained. So this is interesting because if we ever go back to this system, we hope we do, we might see some undiscovered satellites that are very small, so they are very difficult to observe from Earth, but it's very interesting that there may be some undetected satellites orbiting in some resonances in this system. So that is still, we are still looking into it to see if this can survive for the whole solar system age, but it may be an interesting aspect to keep on studying. And last, for the Neptunian system, we we were not able to compare our results with crater counts on Proteus because Proteus was imaged by Voyager 2, but with very low resolution that prevented crater counts from being obtained from this satellite. But for Triton, we did compare to the crater counts, and what we saw was the opposite case than for the Uranian system. We have in mind that Triton is a very special satellite because it's an irregular satellite that orbits in a retrograde orbit, and it is thought to have been captured by Neptune. So this capture can lead to a very large resurfacing process that acts globally on this satellite because the circularization of its orbit can produce tidal heating that may cause this global resurfacing. So in this case, we overestimate the observed craters, as you can see here, for both our indexes in the size-frequency distribution, but this is compatible with this resurfacing process. So we are estimating craters that have already been obliterated. So in this case, when we have an overestimation that is large and is consistent along every crater size, we can compute what we call the surface age or crater retention age. This is a result by Di Sisto and Zanardi from 2016, where in the simulation that follows the scattered disk objects as they become centaurs, The number of encounters of these centaurs with each planet shows a logarithmic dependence over time, and then we can compute what would be the maximum crater retention age for each crater diameter. What does this mean? It means how long can a crater of a given size survive on the surface of the satellite. So here I present the formula just to illustrate that this is the age of the solar system, and this is the comparison between the observed number of craters and the calculated number of craters, and this coefficient is the coefficient of the temporal dependence. So basically what we obtained here, it is very interesting because for different crater counts, you may obtain different surface ages. For the case of the very highly cratered terrain published in 1990, if we think that these observed crater counts are representative of the whole surface of Triton, then a crater could survive on Triton as old as 750 million years, not more than that. But using another crater count that is more recent and is using a general base mosaic count, so it should be more representative, craters can only survive for 300 million years. So in this case, these kind of results can be used as well to constrain the time of capture of Triton. So in general, the study of the surface age is very tricky because it's dependent on the model you use, on the temporal model you use, but we think that we have obtained very interesting results in the case of this satellite. So, as to conclude and give general discussion of what I have presented here, we have in the Saturnian satellite system, we find that our heliocentric model is able to explain the crater counts on the inner satellites, but in the outer satellites, we see that there is an underestimation of the heliocentric model, so the crater counts are more than the ones that we predict, and this could be related to different explanations or different reasons. For example, there may be planetocentric impactors acting in this region, or some other authors have modeled a very early stage clearing of the original Kuiper belt, or as we think it might be a very interesting topic to study, the orbital migration might be very important in this system and might cause the orbits of the satellites to move very far away. So in this case, we are still studying this, and it's very difficult to model migration because we don't know if the rates that are seen today in the satellites are constant or if they change over time. So it's a very difficult but a very interesting topic to study. For the Uranian satellite system, what we saw is that the heliocentric model was not able to match the observed crater counts on these terrains, especially on Umbriel, Titania, and Oberon, that are the outermost classical satellites. The crater counts on these terrains, even though the Voyager 2 images did not have the highest resolution or the highest coverage of these surfaces, it is interesting to see that they are very highly cratered and look very ancient. So in this case, we started looking into the planetocentric impactor model, but in this case, when you want to model a planetocentric impactor population, you need an event that will create the amount of debris that you need. And not every event can generate the debris that you need. So in this case, we looked into Manchin-Wall's paper and publication, and it was very interesting to see that even with some variations, you can build a planetocentric model that suits and fits the observed crater counts with very interesting and promising results that we are still looking into. And last, for the Neptunian satellite system, we do not have counts for Proteus, so it is difficult to see and to assess if the heliocentric model is suitable for this system. But for Triton, with the heliocentric model, we obtain compatible results with the capture of Triton and the global resurfacing post-capture. But we are not really sure if this model is suitable for irregular satellites like Triton, because our model considers the orbits of the satellites fixed in their current orbits for the whole solar system age, which is not the case of Triton. But instead, we can use our model to constrain the time that Triton arrived or joined the Neptunian system. And in the case of Proteus, our model would be more suitable because it's a regular satellite, but we are hoping we can have crater counts for these satellites in the future, with a future mission, for example. And in general, what we see in these systems is that each system is unique and has their own parameters and characteristics, and maybe there may be planetocentric impactors acting in each system, but the heliocentric impactors are present in every system. So it is important to keep on modeling the size-frequency distribution of the heliocentric impactors and the parameters that characterize this population, because this is present in every system, and we have to keep on assessing what is the real role of the heliocentric impactors. So that's it. Thank you very much.
Thank you very much, Natalia. Very, very interesting work and very dense. A lot of studies and peculiarities for each system. So each system you had to deal with different possibilities, and it's really, really great work.
Thank you. Yes.
Now we are open for questions or comments. So anybody would like to make a question or a comment? Okay, Rogério, please.
Hello. Hi, great
Hi,
talk.
how are you?
Nice
Thank
to meet
you.
you. So, Rogério from Southwest Research Institute. Did you consider any type of crater erasure in your measurements as well?
In our model?
Yeah.
No, because it's very difficult to model the erosional processes. As you know, for example, Enceladus has local erosional processes, so you would need a very specific model for each terrain to include in a cratering model. This can be done in some cases, but they are very specific cases where it has been measured for a very long time. What would be, for example, the rate of deposition from E-ring particles on the surface of Enceladus? And it can be done, and it's very interesting to look into that. But as I know, it hasn't been done yet to that degree of detail. But so it's difficult, because sometimes you don't even know if the crater counts are specific enough to do that measurement, you know.
I see. And one more question.
Yes.
So for the Uranian satellites, so you were assuming that eventually planetocentric impactors should dominate.
Yes.
But even though they actually reproduce the size-frequency distribution, would they also reproduce the spatial distribution that we see in the surface?
The spatial, you said?
The spatial distribution of craters in the surface.
Well, the thing with the outer Uranian satellites is that Voyager 2 was able to image small portions of their surfaces. And we are assuming that those small portions and those crater counts for the small portions are representative of the whole surface. That is why we would need to go again to these systems, because it's really interesting to know if actually these surfaces all look like that, or maybe you have a different type of terrain for the part that was not imaged. So we are making some assumptions here that are, for example, assuming that the imaged portion of or area of the satellite is representative of the whole satellite. So that we don't know, and we cannot know until we go there again or have better image resolution.
Sounds good. Just
Thank
one
you
more
for your
question. So
yes,
no,
yes.
it's- Just one
Yes,
more
yes.
question. So
Yes,
no,
yes.
it's-
I love questions.
Yeah, okay. I'll let some other people ask as well. So for the Saturnian satellites, when you
Yes,
put migration plus planetocentric, you're talking about the migration of the satellites or
yes.
the
Migration
giant
of
planet? Okay.
yes, orbital migration of the satellites, because there are works that model this migration to be very important. For example, for Titan, there is a work by Shane Fuller from 2016, I believe, that gives a rate of 11 centimeters per year for Titan. So it's a lot. If you integrate that over time, it would be like a 300,000 kilometers difference in its orbit. But we don't know if this is an extended time that it happens, or it happens, recently. We are not really sure how to model that migration, but it's very interesting, and some authors believe that it's very important in this system.
Thank you.
Thank you.
Okay, thanks, Rogerio. Anybody else? Any other comment or question? Okay, I have actually it's a question mainly concerning Triton.
Yes.
So as we see the best image of Triton, we clearly see a huge resurfaced area.
Yes.
So does that compromise the data? I mean, in terms of crater, how do you deal with that?
Yes. Well, the crater counts that have been detected on Triton are from 2007 using Voyager 2 images that, didn't have a very high resolution. We are even lucky to have some image at all, because this was a long time ago. It was in 1989 with the cameras at that time. And also Voyager 2 did not orbit these systems. It just flew by these systems. So it only had I think that 5 hours for the Uranian system, something like that it took images during that time. So it was a very short period of time. So crater counting in this type of images that have very low resolution is not very reliable, but we think that for the larger craters, the error may be less than if you want to count very small craters on this type of images. Also, the angle of illumination can affect the crater counts. So these are experts that do these crater counts, and as we move forward in time, there are many techniques to recalibrate the images and obtain better results as the ones obtained in the Uranian system. But we think that, again, without going again to this system with an orbiter that can have better resolution images, it's very difficult to assess the whole evolution of one system given an image, of low resolution. So the crater counts that we use are between those publications between 1990 and 2007. But this year there was another author which published another crater count for a very specific area, which is not representative of the whole satellite. So people tend to work with this and rely on the crater counts and the expertise of the science that was made to do that. So we think that if we do not have anything else to work on, we can rely on these crater counts for now and expect them to be, detailed enough to do the science that we are doing. But it is true that these kind of surfaces that show global resurfacing processes are difficult to study. Yes, but well, the craters that are seen, we believe that they are actually there still.
Okay. And also you made this quick comment on the, you can make some constraints with the about Triton and its capture. Can you
Yes.
give a little bit more on that? What can you
Yes,
say?
that is because when you this plot here, or this formula here, but this plot shows how long can a crater survive on Triton. If we take just the blue curve, because we think that these crater counts are more representative of the whole surface, you can say that a crater can survive for 300 million years or less. And this we have checked with other publications on the surface age of Triton, and they are giving similar ages. So when you have this kind of constraint, you can say that Triton in its current orbit has been there for 300 million years or less without having resurfacing processes that can affect the larger satellites. So essentially, you say, given its current orbit, its surface is representing the crater rates that are for that current orbit for the last 300 million years. So if Triton was before that time in its current orbit, it was suffering global resurfacing processes, and the surface was melted multiple times and erased all the craters. Or maybe Triton was not there 300 million years ago, and it was arriving to the system, but we are not sure when Triton was captured, if it was captured at all. That are all possibilities, but that kind of measurement gives you a constraint on how long has the satellite been here without major resurfacing processes that can erase the larger craters. You know that Triton has only the largest crater on Triton is Masomba, which is 25 kilometers wide, and you would expect in Triton to have a crater of 200 kilometers, so 10 times the diameter. So essentially, Triton has had global resurfacing processes during this circularization stage of its orbit, but this process can happen in this orbit or outside this orbit. But essentially, this was 300 million years ago or longer ago. That is the kind of constraint that we can apply to this system with these current crater counts. I don't know if it's clear, the answer.
Okay, no, it's clear. Okay,
Great.
Good, interesting. Okay, anybody else? Any question, any comment? No? Okay, so thank you again, Natalia. Fantastic.
Thank you very much.
Thanks for the presentation.
Great. Thank you. Thank you all for the attention. And you can write me if you have any questions or comments, no problem. And thank you. We'll be in contact.